Welcome to this talk about embedded Linux. Yeah, let's come back to that. So I've been doing stuff with Linux, embedded Linux, for too many years. And interesting enough, when I came to Linux, I actually came to Linux as an embedded operating system. It was only later on I discovered you could run it on other computers too. So for me, Linux has always been an embedded operating system. And in fact, if you look at the deployment of Linux systems, the vast majority of systems are running on embedded devices. There are a few running on servers, in server farms and such like, and very few on desktops. But the majority use case for Linux actually is embedded. So I want to talk a little bit about what is embedded Linux, and some of the attributes of embedded systems. So first of all, let's open it up to the audience. So what is embedded? How do you define embedded computing? Anybody have any criteria? How would you recognize an embedded system? You, sir. On chip? Yeah. On one chip or two chips? One chip, okay. On chip, yeah. Custom boards? Yeah, embedded systems typically do run on custom boards. At the back? Any product with a computer inside? Right, when the computer is hidden inside. Yes, exactly, yep. Yeah, like that. Anyone else? Okay. Well, here's my list. I think, yes. So this illustrates the problem really that there isn't really a definition of embedded Linux. It's kind of whatever you want it to be. So I've kind of boiled it down to this statement here. So embedded computing in general is just code running on a computer inside a device that you don't think of as being a computer. So yeah, if you look at my laptop, if you ask the person in the street, is this a computer? They're going to say, yes, that's a computer. If you point at your washing machine and you say, is that a computer? They'll say, no, it's a washing machine, but it has a computer inside it. So that's an embedded computer. The tricky one is, what do people say if you say, is this a computer? Most people probably would say it isn't, but blatantly it is a computer. It's a very powerful computer, in fact. So smartphones are kind of the boundary between embedded and not embedded. So some characteristics you can look for. And really, the more ticks you can have in these bullet points here, the more embedded it is. So single use. A typical embedded system is a single-use system. Is not end-user programmable. So typically, I can't load new programs into that system. It's locked down. It does the washing, for example. Embedded systems are often designed for price, particularly kind of consumer electronics, where price is very sensitive. So for this reason, we tend to use low-powered, cheap computers. Power constraints, especially anything that runs on a battery, has power constraints. And then also related to that, but different, power dissipation. In particular, we really don't want to use cooling fans. We don't want washing machine's not a good example in that case, but we don't want doorbells. We don't want a thermostat, is a good example. We don't want a thermostat which dissipates so much power that it warms the room up. So different things. So typically, if you have 3 or more ticks on that box, you probably have an embedded computer. So what kind of computer? So here I've divided it into 3 categories. We have microcontrollers, which really comes to your on-chip, your single chip idea. So with a microcontroller, you have a single chip which contains the CPU and the memory and the storage all on one chip. And these things tend to be very cheap. They can be from a few cents up to a few dollars. And they are used indeed for washing machines, microwave ovens, that kind of stuff. Then flipping to the opposite extreme, we have microprocessors, MPUs. So a microprocessor is a chip which contains only the CPUs and the logic surrounding that. And then you have external memory, storage, everything else is on separate chips on a motherboard of some kind. So these are high power, high performance, in other words, but they also consume a lot of power, and they're quite expensive. And they're typified by PCs, the PC architecture. And then we have the third category, system on chip, SoC, which is maybe a little bit of a combination of the two. So a system on chip contains a microprocessor, and also some on-chip peripherals. So typically that would, well, these days at least, it would include a GPU, a video processing unit, USB controllers, I2C controllers, everything that you'd need, particularly for a smartphone. But it does not include the RAM. The RAM and the storage are separate. That's the key point, really. And the system on chip market in this way is pretty much dominated by ARM at the moment. So if you are designing a product based around these system on chips, you have several choices. This actually also applies to x86 and the kind of MPU market. So you can start off with an SBC, a single board computer. So this is something which is a board. It has everything you need, except you just need to plug in power and some peripherals, keyboards, USB, whatever. But it's then fully ready to go. So Raspberry Pi is an obvious example of that. Also your PC. Then we have the system on module, SOM. So a system on module is an SoC, usually, although you can also do system on modules with Intel-based systems. But the key idea here is that you create a little compute board with some kind of connector, either an edge connector or some kind of connectors underneath you can plug into a baseboard, and then you put your custom logic onto the baseboard. And the win here is that the expensive part of designing one of these things is designing the CPU board itself, because that has high frequency electronics on it, which is tricky. You have all kinds of design rules. You need complex PCBs with 10, 12, 14 layers. That's quite expensive, especially in small volumes. So you do all that complicated stuff, or rather the system on module vendor does all that complicated stuff for you, and then you plug it into your baseboard, which is just a simple 2 or 4 layer PCB, and there you put your low frequency electronics on top of that. Yes, question? I think I have one in the next couple of slides. Yes, I'll come to that in a moment or two. So the SOM is great for small volumes of maybe a few thousand units a year or something. And then we come on to fully custom hardware, where you start from scratch and you design the board, including the CPU and the high-speed peripherals yourself. Requires a certain design skills to be able to do that, but I mean, it's not that hard. So, SOM. So this is a typical system on module. This is actually from a company called Phytech, but you can also go to Torodex, Verisight, Contron. There are hundreds and hundreds of companies doing these system on modules. They're mostly not huge companies. Size, it's obviously smaller than it shows on the slide, kind of credit card size typically. So this particular one is a NXP IMX8. So it's a quad-core, fairly lightweight ARM processor these days. Various configurations from between 1 and 8 gigabytes of RAM, up to 64 gigabytes of flash. It has a GPU built in, it has video processing, has a display controller, even has a little MCU built in. It has a little Cortex M4 MPU built in, so you can do some real-time stuff on that if you wish. It's got Ethernet controllers, Wi-Fi controllers, Bluetooth controllers, various display options, and peripherals for USB, PCIe, and various other things. So that's a very typical SOM. They cost, I don't know, $100, $200, something of that sort. Okay, so that's the hardware view of things. Yeah, what about Linux? Well, okay, let's first of all deal with MCUs, microcontrollers. Basically, microcontrollers are not powerful enough to run Linux. So most microcontrollers have at most a few kilobytes or maybe hundreds of kilobytes of RAM and maybe up to a megabyte of flash memory. Nowhere near enough to run Linux. So they run a real-time operating system such as Zephyr is the current flavor of the day, FreeRTX, NutX, and a bunch of others. So when we're talking about embedded Linux, we're really talking about the MPUs and also the system on chips. And these are the kind of things that are going to be running Linux in and around your home. So this is a vehicle system. This is an IVI system, I think this is a BMW system, if I remember rightly. It's going to be running Linux. All modern vehicles are running Linux in the head unit. TV set-top boxes, smart TVs, smart thermostats, not smart thermostats, smart doorbells, routers, security cameras, they're all running Linux. Why? Why do I need to run a 32 or 64-bit Unix operating system on my TV? For God's sake, it's a TV, it just shows pictures. And the answer is that the TV of today is not the TV I was using many years ago in my youth. They have changed a lot. So it comes down really to, first of all, Moore's law. Moore's law applies equally well to embedded systems as it does to desktops. So the chips are getting exponentially more complex for a given price point. And so you need something complex like Linux to control this device and to give you the connectivity you need. So you need a good networking stack. You need connectivity over wireless interfaces of various sorts. You need support for USB and Bluetooth. All of these things, they come more easily if you take a Linux system which has all this built in. So we need a complex operating system. Which operating system do we choose? So the advantage of Linux, first of all, it's free. So I'm using free in the sense here of freedom. You have the freedom to take the source code, to examine the source code, to modify the source code, and to customize it in any way you wish. It's open source, in other words. Next is functional, meaning that Linux these days has support for pretty much every piece of hardware you can imagine. It has constantly been updated. It just works in most cases. And then finally, free, whoops, wrong button. Free in the sense of you don't pay anything. So it's open source, therefore you're free to download the software and build it into any product you want, no charge to pay. So these are all pretty compelling things. And this is why essentially Linux is the dominant operating system in this market. So let's move on from this then and say, okay, my boss has just given me a board, and he says to me, build Linux and make it run on this board for me. So what would you need? Well, first of all, it has to have a 32 or 64-bit processor. It needs memory management. So Linux is a virtual memory system. You need a system with an MMU. So that rules out some of the Cortex-M systems from ARM, for example. So typically they're the ARM A class, the application processors, also x86. RISC-V is becoming more and more important, plus about a dozen others which are less used these days. How much memory? Actually not that much. If you simply want to boot a Linux kernel and maybe get a command prompt, you can do that in as little as 16 megabytes, just about. How much storage? Again, if you just want a Linux kernel and just a simple BusyBox-based system, you could actually do that in about 4 megabytes. Actually, I haven't tried this recently, but certainly that worked about 5 years ago. And you can even go smaller. So people have tried to shrink Linux down, really in order, as part of the IoT revolution, or whatever you want to call it, people have tried to put Linux onto microcontrollers. And it is just about possible, but it's it requires non-trivial effort to start with, and you end up with something that's not easily maintainable. So really and truly, these are the very minimum numbers you could reasonably expect to get to. Having said that, most of the devices you're going to be running have far more memory and storage than those numbers. So that's not usually the big issue. So looking at now the general ecosystem for open source in general and Linux in particular. How does this all work? So first of all, we have what I call the open source community. So these are the various open source projects that you need in order to build your basic system. So obviously that's going to be Linux, but also the compiler support and the libraries you'll need to go with it, the bootloader, and a bunch of other things. So even for a minimal system, you are going to need to draw from, I don't know, 100 or so different open source projects. Each one of these is governed in its own way, but each of them is funded in its own way as well. So these people aren't working for nothing. These people are being paid by somebody. Very few people do stuff for nothing. So this is the community. It somehow works. Nobody knows entirely how it works, but it does work. Then we have the SoC vendors. So these are NXP, Qualcomm, TI, and all those people. So they take this open source code, in particular the Linux kernel, and they put a lot of effort these days into making sure that Linux works well on their chips, because they know that's what people are going to be running. Then the SBC and SOM vendors, and also the custom, if you're doing your own custom hardware, you'll take the output of the SoC vendors and use that, or they use that in their own implementations. And then finally, there are also a whole bunch of people who will sell you support and consultancy along those lines, and send me an email and I'll let you know what my rates are. Pain points. This is not a seamless operation. Things go wrong. We still have, despite what I said about hardware support, we still have problems that quite often you get hardware from various places and you discover that the Linux support isn't that great or is kind of missing. So you may have to have some issues, resolve some issues there. So quite often you're faced with a peripheral from maybe a Chinese vendor with documentation maybe in Chinese, and you'll have to kind of work your way through that somehow. So it's not obvious. The main thing I want to say here really, and I'm not sure this applies to anybody in this room, is the main issue is that the hardware designers generally don't talk to the software guys when they're designing the board. They just take the cheapest bits they can find and plug them onto the board. And then they give it to us, and we say, why the hell did you choose that peripheral there? We know whoever it is, their drivers suck. Why didn't you use these other guys who may be a couple of cents more expensive, but they do decent support? So really the point of this bullet point really is that it'd be really great, if anybody's listening out there, if the hardware engineers would talk to the software engineers before they finish the hardware design. Okay, next point, the update cycles. Open source software is built on the philosophy of release early, release often, which is a problem if you are building devices which have lifespans of years or even decades in some cases. This is pretty much an unresolved issue. I don't have any great ideas of how to fix this, except you need to do buffering and you need to be prepared to put some effort into supporting your devices once they are no longer supported by the upstream projects or the SoC vendors. And then the final point is really a dig at particularly the SoC vendors, which is that they often don't do a very good job of providing their software. And I've been saying this for 20 years and it hasn't made the slightest bit of difference. Okay, so next point then. Do you use a distro or do you build from source? So by using a distro, I mean using things like Debian or Ubuntu or whatever. So why not? These things exist, they work, there's no compilation involved, you just install the ISO file or whatever into your memory, and anything that's missing you just get using apt or DNF or something. This sounds like a great idea, but for reasons we're going to come to in a couple of slides' time, it actually doesn't work that well. The key thing here really is that native distros generally are built around the idea of native compiling. So if you want to rebuild a package from a distro, you'll have to do that on the board itself, or at least on something that's compatible with the board. And that doesn't fit well with typical embedded development. So normally with embedded development, we actually want to keep the development system separate from the actual target board. And for that, we typically use cross-compilation. So that means we have a development system on our PC, we then cross-compile and then deploy to the target board. That's the more natural way of doing things. So distro pluses, yes, vast number of packages, switch on and go. But the minuses, actually one of the biggest minuses, which I kind of skipped over, is that distros don't have board support for every single SOM, SBC, and SoC. So unless you are using some kind of commodity system, such as Raspberry Pi, you're probably going to find that there isn't a board support package available for whatever distro you choose, for example, Debian. So that's a big break to start with. Native compilation, like I say, is not generally what we want to do. Size is also an issue. You can shrink a distro down by leaving out stuff. So a typical distro, when you install it from the net, is going to be 4 or 5 gigabytes or something. You can shrink it down to maybe 500 megabytes. And in the case of Ubuntu, they actually do a pre-packaged version of that called Ubuntu Core. And Debian have also a similar thing, which I've forgotten the name of. But these are still several hundred megabytes. Sometimes that's too much. Sometimes we maybe only have 256 megabytes to play with. So we can't afford to use all that up just on a distro. And then there's a problem with how do you update these things in the field? For reasons we'll come to in a couple of slides, well, towards the end of the presentation actually, doing package update using apt or DNF isn't really very robust. So as you can tell, I'm not a big fan of using distros. There are cases when it does work. So embedded PCs, so things based on x86, little SUM boards or little SBCs based on x86, these often are running some kind of distro, Ubuntu, for example. And also with Raspberry Pi, like I say, Raspberry Pi is used a lot in embedded using this thing called the Raspberry Pi compute module. So the CM, the compute module, is basically an industrial version of the Raspberry Pi. And people using that, they're probably going to be using Raspberry because that's the obvious thing to use. And the key thing is that in all these cases, these are mostly low-volume systems where human intervention is possible if it goes wrong. So there'll be somebody there to hit the reset button when it doesn't boot. Okay, next topic. Let's talk a little bit about BSPs. So board support package. This is the stuff you need to make your board work. So the BSP, you need a bootloader. So you need something that will actually get the thing running to start with. You need Linux. You need a Linux kernel that is built for your particular hardware and particular board, perhaps. So typically that's going to be the vendor kernel from your silicon vendor, be it Qualcomm or NXP or whoever. You'll need some kernel drivers. So if your board has some specific peripherals, you may need kernel device drivers to make them work. You'll need a device tree. Talk about device tree in a minute, but you'll need a device tree to make it work. Then there may be some vendor-specific libraries. Particularly for graphics, you typically will need OpenGL libraries. OpenGL libraries are specific to a particular hardware. And you may also need some GStreamer plugins using codecs built into the hardware. Then you need some boot scripts. And finally, you may need some firmware. So a lot of these SoCs actually contain a number of microprocessors, typically doing things like Wi-Fi and Bluetooth and such like. And you need to load the firmware into those before they're going to work. So where's that firmware going to come from? Probably not. You're not going to write it. It comes as a binary from the SoC vendor. So all of this stuff together is what I call the board support package. So in terms of architectures then, for ARM and other architectures, you need all these components. Plus, if you're using something like Yocto or Buildroot, you'll need the recipes to make all this work. So that's quite a lot of effort. If you're working on x86, things are slightly different in the x86 world. Essentially, the board support package is the BIOS. The BIOS is provided for you by whoever made the board. So typically, you take your embedded PC, plug it in, it will at least boot up into the BIOS. As well as the BIOS, there may be some additional stuff. You may have some custom kernel drivers and such like. But because the PC environment is so standardized, most things will work pretty much out of the box. Okay, next topic. So I want to go back a little bit and talk about the fundamentals of embedded Linux. And I want to talk about the 4 essential elements of embedded Linux. Actually, this applies to any Linux system, even for PCs. For any system, you need these 4 things before you can get any work done. So I'm going to talk briefly about toolchains, bootloaders, kernels, root file systems. So you need a toolchain. You need something that's going to compile code for you, for your target system. Could be GCC, could be Clang, doesn't really matter. Next, you need a bootloader. So the bootloader is the thing which, from power on, takes you to the point where you can run Linux. And as we just said, in the case of x86, the bootloader essentially is the BIOS. Or at least the BIOS is part of the bootloader. You need a kernel. You need something to, you need to get a version of Linux which is customized for your particular hardware and board. And then finally, you need a root file system. The root file system has the user space components, which are the init system and the libraries and shells and shell scripts and just basic daemons. So toolchains. I'm not going into too much depth on this, but essentially a toolchain is, it's not just the compiler, it's also the linker. You need a C library, and you probably need a debugger unless you are going to go without debugging stuff. In most cases, the compiler, the linker, and the debugger is going to come either from GCC or from Clang, or you can actually mix and match if you want to. When it comes to the C library, you have two choices. You can either use glibc, which is big and fully functional, but maybe a bit too big in some cases. Or you can use muscle libc. Muscle is a smaller C library, handy for smaller format systems. Toolchains, native, cross-compile. I think we've covered this already, in fact. You need a bootloader. So a bootloader is, actually the bootloader does a number of things, which I don't think I'm differentiating here. So the bootloader does two fundamental things. It has to do the initial boot of the board. So when the bootloader starts to run, the board is not fully set up. So it will include some initialization code to set up the CPU and peripherals, maybe set up the SD-RAM controller, all kinds of weird stuff. So there's a whole bunch of early initialization stuff that is part of the bootloader. But then its main job, once it's kind of got the system up and running, is to load a Linux kernel into memory and set that running. So bootloaders. The most common one is called das U-Boot. So U-Boot has been around for a long time, and it has support for thousands and thousands of different boards. So U-Boot is probably a good place to start. There's one called Barebox, which essentially is derived from U-Boot, but takes a slightly different approach to things. It's a little bit specialized, but people do use it. There's one called Little Kernel, or LK for short. Little Kernel is relevant if you're using Qualcomm devices. So Qualcomm use Little Kernel exclusively as their bootloader. And I think a couple of other manufacturers do. I think MediaTek do, for example, maybe Rockchip, I don't quite remember. And then for x86, use Grub. So I said the bootloader is the BIOS, which is correct. So the BIOS does the early initialization stuff. You still need something that's actually going to load the Linux kernel, and that would be Grub. And there's some alternatives to Grub, but that will do for the moment. And then you need a kernel. So non-x86 boards seldom use mainline Linux. In other words, mainline Linux generally doesn't have support for the SoC you happen to be running. So you need instead a vendor kernel, which means you have a dependency on your SoC vendor. And that will then have code to initialize the chip and set things up correctly. May have some extra features. So Qualcomm, for example, has this thing called energy aware scheduling, which is a whole bunch of code. And there may be some other peripherals needed. This, like I say, is a pain. One of the pain points is that the vendors don't update as often as mainline Linux does. So typically they only give you one update per year, not the 4 or 5 that you get from Linus Torvalds. Also, vendors are not very good at pushing their changes upstream. So good old Qualcomm, for example, I haven't checked this figure actually in about 5 years, but about 5 years ago, they had 25,000 patches on top of mainline. 25,000 patches, that's over 1 million lines of code. That's a lot of code. And then still part of the still part of the board support package, you're going to need a device tree. So hands up, who knows what a device tree is here? Just a matter of interest. Oh, okay. Looks like maybe a third, which is good. So device trees, why do we need a device tree? So the thing is, Linux, when it boots up, it needs to know what hardware is running on top of in order to know what device drivers to load and how to configure those device drivers. So how does it work this out? So in the case of x86, we have the BIOS, and the BIOS has things called ACPI tables. So ACPI has some basic information about the peripherals on the motherboard. So Linux reads the ACPI tables, it can initialize those peripherals. And then for everything else, we have PCI. So all the other peripherals on a PC are going to be attached to the PCI bus. So we just go through enumeration cycles on the PCI bus, and we read back the configuration for every single function on the PCI bus. And from that, we can identify the hardware and also the resources it's using, and we can initialize the device drivers. However, embedded devices don't have BIOS. Embedded devices don't have PCI, or at least not as the core part of the system. There may be PCI added on afterwards, but it's not part of the core. So in that case, we have a thing called a device tree, which is a data structure, a tree, obviously, which describes the hardware components. And everything apart from Intel uses device trees. So ARM, RISC-V, PowerPC, MIPS, everything else. PCs, x86 is the exception here. And then finally, out of my four things, we have the root file system. So the root file system contains the user space part of your system, and that at the very least must contain an init daemon, because once Linux has stopped booting, it will want to run the init program, and then it hands over to user space. So at the very least, you need an init daemon, and then all the libraries that depends on, and then the executables for the daemons that's going to start up to do networking, authentication, logging, everything else that you have to do. So all of this stuff has to be put together somehow. You can do it by hand. If any of you have ever done Linux from scratch or embedded Linux from scratch, you can do this by typing commands. And to be honest, I quite enjoy doing that. It's quite fun once. But the third or fourth time, it gets a little bit tedious. So that's literally how we did do it in the early days. But since about 2010, we've had some pretty good build systems. And nowadays, we can just throw things at the build system, and it'll do everything for us. So build systems, we have BuildRoot, OpenWRT, OpenEmbedded, Yocto. Of that bunch, Yocto is by far the most commonly used. But they all have their niches. So BuildRoot. BuildRoot actually is the oldest of those build systems. It's the oldest build system that's still being used and maintained. And it supports pretty much everything you want. It supports, it has about 2,500 packages, board configurations for a couple of hundred boards, and so on. So BuildRoot is actually quite nice. It's menu driven. You just go to scroll through the menus, select the things you want, and then you just type make, and it goes away and builds it all. The snag with BuildRoot, however, is it doesn't really scale very well. The way the data is stored means you can't easily share that data with someone else. And so if you have a team of more than a few people who are working closely together, then you rapidly find the point that where BuildRoot doesn't scale. So BuildRoot's great for small systems. It's really great for demo projects and things, but it's not really for complex tasks. OpenEmbedded then, OpenEmbedded started a little bit after BuildRoot, and it has a couple of useful concepts in addition to what Buildroot has. The main one really is this concept of layers. So a layer contains a bunch of recipes. Recipes are basically, a recipe is the instructions to build something. And if you've just been through my previous presentation, you'll know exactly what a recipe is. But the key thing here then is layers allow you to easily move chunks of information, recipes, from one environment to another. So you can share this between different departments in an organization. And there's also third-party layers for useful things like the Qt libraries or SE Linux or whatever. And you can just kind of incorporate those. So part of Open Embedded is something called Open Embedded Core. And this you'll see in a moment why I'm talking about this. So OE Core is the minimum you need to make Open Embedded work. And it's used by various projects. The key one is the Yocto project, which I'm coming on to the next slide. But also various other organizations use OE Core to create their own build system. So that brings me on to Yocto project. Now, Yocto project then is a Linux Foundation sponsored project. And because of the kudos and the marketing and the whatever that gets, Yocto has become the main way that people use in order to get Open Embedded, in order to build reliable systems. So most people talk about Yocto project, which is just an umbrella around various components, including Open Embedded. So if you want a definition, Yocto project is OE Core plus BitBake plus Pocky, which is Yocto project specific, plus some reference BSPs, bunch of documentation, and a graphical user interface, which nobody ever uses. Okay, so that was it about build systems. Any questions about that? I'm kind of going through this and burbling on a little bit. This is kind of a bit of a random selection of things. Anybody, any questions on the stuff I've done so far before I go on to the next thing? Or you can wait till the end. Yes, sir. Oh, people use all kinds of languages. So the basic operating system is built in C and C++ because that's how it's written. But Rust is also becoming significant there, I think. But when it comes to the application layer, so I'm not really talking about the application layer here, I'm just talking about the operating system layer. But when it comes to writing applications, Python is pretty popular. It's a nice language to work with. People use JavaScript, Node.js, and all that kind of stuff. Not quite sure what I think about that. But you can also write in Go and I don't know. If there's a language, there's support for it somewhere. So I would say that the application level these days is mostly written probably in Python and various flavors of JavaScript. Yeah, but you can use C++ if you want. Depends what you're doing. I mean, certainly when it comes to the graphical layer, so the graphics is mostly written using Qt. You can use QML, which is the description language which sits on top of that. But Qt is inherently a C++ library. Sorry, did anybody else have any questions? I have to keep coming over here because if I stand there, I get blinded by that light. Look, oh yes, get back. I would like to know the answer to that myself. So the question is, why are silicon vendors so bad at pushing code upstream? I could say all kinds of things which could be inflammatory. But I think the truth is that and this is not just silicon vendors, but hardware vendors in general, they are kind of focused on shipping hardware. And to them, software is not their priority, so software is just a drag. They don't make money, at least they don't make money from selling Linux. So there isn't a huge incentive for them to do a particularly good job there. The incentive is simply to do a job that's good enough to be able to sell the product. Anything more than that is hit and miss. So I think that's the fundamental reason. It's kind of an economic thing. The best thing you can do as consumers of this is to refuse to buy the silicon unless they fix the bugs. Unfortunately, you have to be a really big player for this to have any significance. But if everybody were to do this, if you were to vote with your feet and say, no, I'm not using your chip because your support sucks, that would maybe persuade them to do better support. Again, I've been saying this for 20 years and it hasn't made the slightest bit of difference, so I don't expect this to really happen, but it would be nice. Exactly, yes. I mean, in an ideal world, all of this stuff will be upstream, and I would just be able to go to mainline Linux, kernel.org, download their kernel, and it should just work. And that does work pretty well for x86, but it doesn't really work for anything else. You just have to live with it, I'm afraid. Okay. Oh, sorry. Yeah, so Raspberry Pi is popular in embedded, even though it's not a particularly good embedded processor. So in the grand scheme of things, you would not use a Raspberry Pi because, well, for various reasons. However, because it is commodity hardware, it's commonly used, it's well supported. There are whatever tens of millions of them in the system. Then people do gravitate towards Raspberry Pi for embedded systems. Hopefully they're using the compute module, because I really don't like the idea of a Raspberry Pi with an SD card in there. Running an operating system off an SD card is not a good idea. SD cards are not robust. Whereas the compute modules have eMMC memory, which is robust. So if you're thinking about it, don't use a Raspberry Pi per se, use a Raspberry Pi compute module. They are industrial quality. Okay, so moving on then, I've got a couple more things to do. Not very much actually. Real time, open source, and that's it. So, real time. So, in many people's mind, embedded and real time are kind of commingled as being kind of the same thing, but really they're not. So I feel nevertheless compelled to talk a little bit about real time here, just to clarify a few things. So first of all, real time means that you have a computation which must be completed by some deadline. So examples, anything to do with motion control, that is inherently a real-time task, because you need to decide the speed and direction of the robot, or the robot arm or whatever, within the next second or something before it hits something. So you have to continually recompute where you are and where you want to be, and then set the wheels in the right direction. So that's a very obvious real-time thing. Also, we have things like displaying a video stream. So video is a real-time thing. You get a new frame, 30 or 60 or whatever frames per second. So you have one frame period in order to take that frame and display it on the screen. So that's a real-time task. Anything that doesn't have a deadline is not real-time. So for example, compiling a program is not real-time. We would like it to happen as quickly as possible, but if it takes a minute or an hour or a second, so long as the compiler is correct, then the output is just as good. So there isn't a solid deadline as to when that compilation has to complete. So we can talk about real-time metrics. And really, when it comes to real-time, what we're really talking about is determinism. So it turns out that computers are highly non-deterministic, despite what it says in the books. And if we look at a typical graph, so we have some event happens at t0, we have a deadline called td, and these lines here are meant to represent when the output was ready. So you can see, first of all, there's a range of times when the output was created, and we call this the jitter. So this is the variance in creating and computing the output. And in this example on the slide, this is a not very well-behaved real-time system because we have some cases where we miss the deadline. So that means that the system failed to some extent. So in order to make this system real-time, what it really means is we need to take this graph, we need to move everything over to the left, and we also need to reduce that jitter, so we need to reduce the length of time here, or the variance of time here. So like I said, there are two things to consider. First of all, how long is it between T0 and TD? If this is a millisecond, then that's quite tricky. If this is like 10 seconds, then anybody can do that. So shorter deadlines are harder. The other thing which people often forget is, how much do you care? How much do you care about missing the deadline? Does it really matter if we sometimes miss the deadline? The more you care, the harder it is. And ultimately, if you care absolutely that we must never miss this deadline, it's actually quite difficult to prove that your system will never exceed the deadline. The only way you can really do that for sure is mathematically. And in order to do a mathematical static analysis of a system, you need something that's far simpler than Linux. You need basically a bare metal MCU type system. So that's why actually most real-time computing is not done on powerful application processors. For real-time, we tend to use MCUs, microcontrollers. Microcontrollers, you can write them bare metal. You can write simple polling loops, which have guaranteed response times. That's how you do real-time. Nevertheless, there are some real-time things that we can't avoid on a Linux type system. So we often talk about soft and hard real-time. So with soft real-time, we're a little bit relaxed about missing the deadline. And a typical example of this is some kind of video processing. So nobody's going to notice if you miss a sample now and again. It's not good. It's not a good thing, but nobody's going to die, and probably the end user's never going to notice the odd frame missing. So we can be fairly relaxed about this. As long as we can hit the deadline 99% of the time, or 99.999% of the time, or whatever, we're okay. The tricky one is really the hard real-time thing. So missing the deadline is never acceptable, because missing it means that something has gone wrong. You may cause some damage to some equipment. In extreme cases, you may cause injury or death. So you can imagine the braking system of a vehicle. As we said the other day, it's no use if when you press the brake, you get a little waiting symbol waiting to apply the brakes, and then apply the brakes, but it's too late. There is this famous quote by Linus. So he says, controlling a laser with Linux is crazy, but everybody in this room is crazy in his own way. So I think that probably applies to us as well. So if you want to use Linux to control an industrial welding laser, blah, 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 I have no problem of you using preempt RT. I'll talk about preempt RT in 2 slides' time. So what can we do about real-time and Linux? So I'm going to talk about user space and kernel space. So first of all, in user space, the key thing, of course, is you use real-time scheduling. So Linux has multiple scheduling policies, but the key ones are sched normal and sched FIFO. So sched normal is the default. It's what we call the completely fair scheduler, and it guarantees to have to give each thread a fair share of the CPU. But obviously, it is not deterministic. Then we have sched FIFO. So this is a priority-based scheduling algorithm. We have threads with priorities from 1 to 99, with 99 being the highest. And the algorithm is quite simple. The scheduler prefers to run sched FIFO. So it will run all the sched FIFO threads until there are none left, and it runs them in priority order. Only when there is no real-time threads do we run the normal threads. So the real-time threads always preempt the normal threads. So your real-time stuff, sched FIFO, the non-real-time stuff, sched normal. Also, when it comes to Linux, as hinted by the comment from Linus Torvalds, the key thing here is preemption within Linux. So Linux is a source of non-determinism, caused mostly by scheduling latencies caused by interrupt handlers and locking algorithms and a few other things as well. You can change the behavior of Linux by setting kernel preemption. So first of all, you can set config preempt. That means the kernel is now preemptible, which means that if we get an interrupt whilst we're running kernel code, we will respond to that interrupt and maybe do a reschedule and then run a high priority thread. So that's fairly non-controversial, but it's not turned on by default on some systems. So, but it is enabled on most embedded kernels. It's not enabled on desktop systems. So that's good. That gives you jitter of the order of milliseconds, maybe tens of milliseconds, but it's not too bad. And then we have preempt RT. RT stands for real time, obviously. That does a whole bunch of things, which makes Linux far more deterministic. And you can get jitter of the order of hundreds of microseconds, or even tens of microseconds in some cases. So this is approaching quite a good real-time system. Why don't we enable these things by default? Well, because they slow the system down, actually. Real-time is not fast. Real-time is deterministic. If you want a fast system, you want it to be non-deterministic. And that's the thing that people often mistake. So the more deterministic your operating system is, actually the slower, the fewer number of bytes you can process per second. Almost out of time, but I've got like 3 slides to go. Quick word about software update. We need to be able to do atomic updates. And you cannot do atomic updates using things like apt and DNF. So package managers are of no use here. If you get a power down halfway through an apt update, you're going to corrupt the system. That's fine if it's a desktop. You can hit the reboot button. You can, if necessary, type some things. But if your system is on the seabed or on a mountain or somewhere else inaccessible, that's of no use. So we tend to do redundant images. So you have AB images. You boot from the A partitions, and then you apply the update to the B partitions. When the update's complete, you flip the flag. So next time you boot from the B partitions, and then you'll update the A partitions, and you just ping pong between the two. So that's a very common way of doing things. SW update, Rauk, Mender are typical tools for doing this. Okay. A couple of slides about licensing. I'm going through this quite quickly because I know people are probably anxious to make the train. Let's quickly talk about licensing. So we have 2 types of license, essentially. We have permissive and copyleft licenses. The permissive licenses are things like BSD and MIT and such like. They are fairly easy to work with. They basically say you can do whatever you like with this code, except you can't change the copyright and you can't change the warranty. Everything else is fine. And then we have the copyleft licenses, which are the GPL type licenses. Now, these are good licenses. I like them very much, but they do have a bit of a bad reputation. The main difference then is with GPL, it says that you must distribute the source code to your end users. So any changes you make to the source, you must give to your end users, either by just making it publicly available, or you can do a thing called a written offer, which means that if they contact you, you will promise to give them a copy of the source code. There's the LGPL, which applies to libraries, which I'm going to skip over. And then we have version 3 of the GPL, which is the one that gets people really excited. So version 3, which came out in 1999 or something, it's quite an old license now. The key part is this right to tinker. So the key part of the GPL 3 says that you must be able to update the end system with any GPL components. So that means that you must have a mechanism to apply software updates, for end users to be able to apply software updates to whatever device it is. So this leads to the problem then, what happens if I have a secure system and I've implemented secure boot? So secure boot means I'm signing my kernels with some encryption keys, and then the bootloader checks those keys. If they don't match, it won't boot. That obviously is not compatible with GPL v3. So the question is, can you do secure boot with GPL 3? And for a long time I thought it wasn't, but actually I came recently across this talk by Bradley Kuhn and Behan Webster, both of whom I trust as knowing what they're talking about. And this actually is from 2017, so this is not a new thing, but it is to me. So I'll just say, go and have a look at that. But essentially, the short form of this is that, yes, it is possible to have secure boot and GPL3 components on the same system if you do this special, what they call dev board. Where is it? Yeah, if you have this special dev board mode, in other words, we can boot up with a non-secure boot in order to run the GPL components, but you do not probably run the proprietary components, which are going to do whatever it is your system does. So you can boot up, you get a shell prompt, but that's it. And that's the way the TiVo set-top box works. You can actually boot a TiVo set box with your own kernel, but it won't actually stream any video. Okay, apologize for running over. I didn't realize I had quite so much to say. So just a quick conclusion then. Well, the world is run by embedded Linux these days, thankfully. There's a lot of technology involved in doing all this stuff. It's evolved a lot over the last 20 years. And it's been my life, essentially. So the slides are available at this link. You can also contact me via Twitter, and you can link with me on LinkedIn. Okay, so if anybody wants to run for the train, now is a good time to do that. But I'm also happy to hang around for some time to answer any questions. So if you're not in a hurry, feel free. Otherwise, feel free to make a dash.